Today, we will be analyzing and reviewing our catapult, Dragon, aka Dracula. Anyways, let's get on with it.
Problem definition. We have to build a catapult that can launch 6 meters but can also pass the variable test by being able to be adjusted for different lengths,
depending on what roll we get on the dice. Restrictions on this project include being able to find the correct materials and build a working catapult because we're doing the medieval challenge. And also finding time to meet with busy schedules is a huge restriction.
Also, it has to be very accurate as we are choosing a smaller target area.
The catapult has to be within 35 by 35 by 35 centimeters, and this may be difficult, so this is also a restriction.
The real world application is so we understand how to problem solve and accurately follow instructions, and furthermore learn how to construct something using a variety of different tools and methods.
When we reached the brainstorming portion of our project, we drew up some designs to help us visualize what we wanted to incorporate in our actual catapult design. This is what the initial design process of our catapult project looked like. 3 pros of this design were that it was very easy to make, very easy to modify, and portable. But 3 cons of it were that it breaks easily, it was flimsy, and it was hard to change the distance for the variable challenge. All of these factors were taken into consideration in the final iteration of the project. And eventually we decided upon a final design.
So we decided on a design similar to one that we saw in the classroom from prior years, but ours is a little bit different. So ours has a wooden base that connects the arm with 2 springs, and the ball is held in place with wood on 3 sides and a pencil on the 4th side. This design is good because it is sturdy and can launch the ball very far. It is versatile because only 1 spring can be used for shorter distances and launches the ball at an appropriate angle to create an abundance of airtime. This design, although does fall short on accuracy, there is no way to measure how far the arm needs to be pulled back for each distance other than eyeball guessing it at an angle, because we weren't really sure if we had to do it at 3 meters and we had just launched it at 5, that we would release a spring but pull it back a little far, we would just guess, and this could cause issues because we did originally were doing the accuracy and variable challenges.
Although we were nervous to build the design because of the fear that it may not come out right, the final design came out quite well and performed pretty well. After 2 of our trials, the results proved to be, for the first trial, a time of 0.86 seconds, 2.8 meters traveled, 3.87 meters per second initial velocity, 2.8 meters range, a maximum height of 0.682 meters, and a final velocity of 3.26 meters. And for the second trial, the time was 1.35 seconds, the distance traveled was 3.1 meters, the initial velocity was 6.39 meters per second, the range was 3.1 meters, maximum height of 1.34 meters, and a final velocity of 2.30 meters. In terms of what could be altered to make the catapult more successful, the spring tension, length of the launch arm, and the sturdiness could have been changed. By increasing the tension of the springs, more potential energy is brought into the equation, and this equates to a more powerful, longer-ranging catapult design. By lengthening the length of the launch arm, the time it takes from when the arm is let go to when the ball leaves the catapult will be increased, thus resulting in a higher launch velocity. And by using stronger wood or more support beams for the design, the stability and therefore accuracy of the catapult will be increased. Assuming that our catapult was converted to a catapult with a scale of 0.1 meters to 1 meter, the new dimensions of the catapult would be 2.9 meters by 2.9 meters by 3.5 meters. By using these dimensions, the new values of the full-size siege engine would be a range of 70 meters, a maximum height of 11.4 meters, and an impact velocity of 57.4 meters per second, assuming that the launch angle is 45 degrees and the same release angle is used as the release angle responsible for launching the golf ball on the small catapult, a distance of 7 meters. The force that was involved in maximizing the power of the siege engine was spring force, because more springs in our situation equaled more power. And the way in which energy was maximized by launching the golf ball was by having the golf ball leave the catapult at a launch angle of 45 degrees, which was the most efficient launch angle for our specific catapult. All in all, compared to other groups, our design was very successful. We passed both the variable and distance challenges on test day, and also passed the materials challenge. Most other groups did not pass all 3 challenges, but we were able to accurately launch the golf ball 3 meters, 4 meters, and 6 meters, although it did take multiple tries to perfect some of these distances. The first design change would be creating a sturdier holding place for the golf ball. We made ours out of a pencil and tape, which could have easily broken. We also would have created a device on our catapult that measured how far we needed to pull the arm back for each variable distance, because we basically made inferences when it came to how far the arm should be pulled back. Lastly, we would change out one of the springs because they were 2 different lengths, 8 centimeters and 9 centimeters, and this caused the golf ball to not fire straight. Our TV short and catapult will be good for the audience because we show the physics behind our catapult, especially with 2 springs. We also show how physics relates to ancient times because we use an old-fashioned machine and it is made out of old-fashioned materials. Lastly, our show will be interesting because our catapult is so strong it can launch the ball very far distances, which is interesting to the viewer, because who doesn't enjoy watching objects being shot through the air? I know I do. Well, that's all, folks. Thanks for watching.